Okay, so this is the hybridization effects on acid. Remember that anything that increases the stability of a base, right? Anything that increases that stability of that conjugate base is going to increase the acidity of that compound, right? Okay. So one of the interesting effects is that this right here is a hybridization effect where it's going to stabilize that lone pair charge due to that hybridization that takes place. See that? You have a hybridization. Okay. Everybody remembers what hybridization is? Anybody want to try to give me what that is? I know, right? You probably thought you knew, and then you're like, uh-oh. Panic. He made us actually do it. Yeah, so that's one of the things you should always do for yourself, okay? I'm not going to have time to do that on everything. But when I ask you those questions of like, do you know what that means? Try to actually explain it. So within your head, act like you're two people. You're explaining it to yourself, okay? Okay, and what that tests, you can do it very fast once you get used to it, and it will actually test whether you know it or not. Because I promise you, when you're in class and I'm explaining things, you're probably going to think you know about 25% more than you actually know, okay? You're going to feel brilliant and everything will just feel like I know everything. And then when you get and actually have to explain it and use it, you're going to go, oh my God, I don't know anything. What am I going to do? And then you start panicking, right? And things get worse from there. Okay, so that's one of those things that if you do that, then you can go, oh, Dr. Clausen, wait a second. You need to explain that further, okay? Okay, so hybridization here. All right, so if we look at a sp3 orbital here, we can see that this right here instead is an sp2 orbital. See that? And that's what hybridization is. It is hybrid orbitals. Okay? So it's mixing the orbitals of that atom to form hybrid orbitals. Specifically, that would be your sp, sp2, sp3. Okay? Okay. And that exists because these actually have p orbitals that are involved in the double bond, right? See that? That's how you make a double bond. You have two p orbitals and they overlap on the sides. Okay? The s orbital would be the space in between typically. You know, it's a direct connection of two orbitals. And when you need to have multiple single bonds, you typically are going to make sp hybridizations of those orbitals. Because notice most of these structures are not nice X, Y, Z, right? Have you noticed that? Yeah, they don't make like straight perpendicular bonds, do they? Yeah, they're more like triangular shaped, right? Or tetrahedral shapes, right? And tetrahedral shape is literally an sp3 hybridization, maximum separation for those orbitals, isn't it? sp3 hybridization gives you four orbitals. They point in four different directions. Maximum separation would give you a tetrahedral shape, right? Is that making more sense? Fantastic. So what we can see here is that you get a stronger acid with greater S character. Okay? The larger the S character of that hybridization, the stronger the acid typically. Right? And that's the hybridization effect. I know. I kind of did that in a roundabout way because I wanted you guys to really think and get into that mindset where I'm going to actually ask myself, okay? I'm going to try to explain it to myself and see if I understand it, right? Does anybody know the 5 levels of explanation that you should do so that you fully understand something? No? Okay, there's actually 2 versions. There's a 5-level version and there's a 10-level version. The 5-level version is usually good enough for most things, okay? And the 5-level version is essentially you start off explaining it to somebody at your level, and then you go down to younger or i.e. less educated people as you go down, okay? And you have mastery if you can explain it to basically a 10-year-old, all right? Somebody who has their full cognitive abilities but has very little education, right? Okay, so right here we again see that S character. So an SP3 has the least S character in its hybridizations, right? The SP2 has greater S character. SP has, again, greater S character. And what we can see is as we gain greater S character, what happens to our acid strength? What's a lower pKa mean? It is a stronger acid, okay? That's one of the reasons I asked you guys that, because oftentimes people won't connect that because it's, again, a negative log, right? It's a negative log relationship. Okay, so this is the effects of resonance on pKa. And right here we can again see that this one here is resonance stabilized, whereas this one is not. And so resonance stabilization is going to act to stabilize your base here. So it stabilizes your conjugate base. Anything that makes your conjugate base more stable is going to do what? What's the strength of a base? Or another way, what's the stability of a base is the strength of an acid, right? The more stable the conjugate base is, the stronger the acid. Come on, you can. It's okay to have things wrong or mess up. This is where you get to do that. In fact, it'll increase your learning, okay? If you mess up, you tend to remember, and then you'll understand it better. So don't fear messing up or being wrong. It's okay. No problem at all. So again, here we are delocalizing that electron charge. This helps stabilize that electron charge, and that means that proton becomes much less likely to come back on, right? Okay. Is everybody understanding how you logic through these things? By the way, that's always the first step of logic and critical reasoning, is learning the patterns of another. The next step is to internalize and take those patterns and do them yourself, okay? So which is why you get that explanation from me sometimes. All right, so this right here is going to be Lewis acids and Lewis bases. This is the third type of acid and base. This is the one that's the most different in terms of its definition. This is also probably the most important definition of an acid and base for organic chemistry. Okay? You are going to see this show up a lot. If you truly understand Lewis acids and bases very well, then you've pretty much have about a third of the questions in this class answered. Brush your hands, you're done there. Okay? By the way, there are only 3 principles you really need to understand well to do well in this class. The first fundamental one is naming. You need to be able to name the compounds and understand what those names mean, okay? And we'll get into that more because this is still review stuff, isn't it? That's foundational. Next up is Lewis acids and bases. If you understand Lewis acids and bases, those 2 skills right there will let you pass the course, okay? That's it. That's all you need to pass the course. And if you then have, beyond that, the ability to slowly reason out due to electronegativity in what will be a more stable state, then you can pass this course not memorizing a single reaction. I did it when I was in your guys'. That's it. That's all you need to remember. Okay? I can tell you that because I did that. All right? And I got A's, and I was in a class where these tests happened every week, and that was front and back mechanisms. Once we get into mechanisms, you know how awful that is. 6 pages long. So 12 pages of mechanisms every week. Wait until we start doing mechanisms. You're going to go like, Dr. Clausen is so nice compared to the person he took it with. Man, she was evil. Yeah. Okay, so again, Lewis bases. In organic chemistry, these are typically called nucleophiles. Again, see that bold on that term? What does that mean when it's bolded like that? It's important. If I don't know this, I'm screwed. Okay? And so there is a terminology, a language that you need to learn. Without the language, can you actually answer almost any question? No. Have I told you guys how many people I've caught in the process of cheating on the test? And why it didn't matter? Okay, so I've caught 5 people in the process of cheating on tests. Of those people, every single one failed the test completely. And without me reporting it or anything, I didn't need to, failed the class. Okay? And do you know why it doesn't matter if you cheat on a test in chemistry usually? Because usually, if you're cheating on the test, you haven't studied enough to even know the language. So you don't even know what you're being asked. Pretty rough, huh? Yep. So fundamental skill of chemistry is you need to learn the language so you have the concepts to understand the question, right? If you can't understand the question, there's nothing you could do on the test. It's just over. Okay? Okay, so again, Lewis bases, these are called nucleophiles. What does a nucleophile mean? Nucleo means nucleus. You got it. Nucleus is where the protons are, and protons are positively charged. You guys got it. Good, good. And phile means like love. Okay? So they love positive charges. That means nucleophiles must have some sort of center of negative charge, right? Most often it's going to be something with like a lone pair, okay? Another way of saying that is these are species with available electrons that can be donated to form a new bond. One of the key things that is going to tell you this is delocalized electrons. Remember when I talked about that? Those are things like lone pairs, right? Lone pairs are very often going to involve nucleophiles, okay? Those are things with a double bond. Double bonds are pretty good at being nucleophiles, okay? Those are things like triple bonds. Triple bonds, again, is a pair of electrons that can be accessed and attacked, right? Okay. Notice they don't have to have a negative charge, but the powerful nucleophiles do, okay? Lewis acids are going to be species that can accept these electrons to form new bonds. So a Lewis base has electrons to donate. A Lewis acid has a space to accept those electrons, doesn't it? Okay? And so if that's true, then that means the Lewis acid has to accept a pair of electrons. And a good name for that would be a what? Electrophile. Electro meaning electrons, right? Phile meaning loving, meaning I accept electrons. Okay. Note again, this means typically you have a free orbital of some sort, and more often than not, you're going to have some sort of positive charge, or you would have a very high electronegativity. Okay? Typically, positive charge is more common. All right. So again, nucleophile donates electrons to a nucleus with an empty orbital. Electrophile accepts a pair of electrons. When forming a bond, we say that the nucleophile attacks the electrophile because the arrow shows where the electrons go, right? Okay. And so what we do is we draw the arrow so it shows going from negative to positive because that's where we actually have things moving. Okay? Because remember, we can't really move the nucleus, can we? That would be moving the entire atom. We can move the electrons around quite easily, can't we? Okay? Or another way of thinking about this, to pick up your cup, do you move your whole body or your hand? Your hand. Why do you move your hand? Yeah, you only need that and it's light, right? It's light. And so it takes less energy to move something light, doesn't it? Electrons are 10,000 times lighter, aren't they? So they take less energy. So the electrons are what gets moved. When breaking a bond, the more electronegative atom is going to receive the electrons because that's what electronegativity means, isn't it? Okay? It means that I hold on to the electrons better. All right? So when a bond gets broken, the more electronegative ones can pull the electrons towards it. Okay, so right here is a bunch of examples. You can break down, I'm going to say 80%, 70, 80%, but it's actually probably closer to 90% of reactions into this exact same pattern, okay? Longer reactions are typically just repeats of those patterns over and over, all right? So this is like paramount. The better you understand this, the less you have to understand everything else for the rest of the semester, okay? Okay. So right here we see the typical example of a Lewis base attacking a Lewis acid. You typically call that attacking because the electrons are going to it, right? So typically the Lewis base attacks the Lewis acid. All right, so again, another way of representing this is a nucleophile attacking an electrophile, right? Okay. And can you tell which one's the nucleophile without me labeling it? So take your eyes, block that nucleophile, electrophile, and then reset your mind. Which one would be the electrophile and nucleophile between, say, anything with a lone pair of negative charge? Is that a nucleophile or electrophile? Nucleophile, right? Remember, lone pairs, negative charge, the hallmarks of a nucleophile, right? Can't be electrophiles because electrons would get repelled, wouldn't they? Yeah. Anything with a positive charge or a center of positive charge is going to typically be an electrophile. Okay? Can anybody tell me why this right here is an electrophile? Yes, so if we look at this, there's no charge on it. So our positive charge typically means an electrophile, but we don't have that, right? Negative charge doesn't necessarily mean it's a electrophile. Okay? So if we have no charge, it doesn't mean that's one or the other. So if we look at boron, boron has what? Does it have all its orbitals filled? Right here. No, it has an orbital that should be free, right? Okay. That's a hint that says, I have a free orbital, I can accept electrons in that free orbital, right? Okay, what's the other hint that we should look for? That it would have a positive charge at that spot, right? Okay, so if we look at boron versus fluorine, which is more electronegative? Fluorine, and by a lot, right? We're looking at a pretty stark difference. Boron being almost a metalloid, right? Fluorine being the most electronegative thing on the damn table. And there's 3 of them. 3 fluorines all drawing electron density from boron, right? So this is actually about as close as you could get to being ionic, isn't it? So you have this very positive boron here, and it has a free space to put electrons, right? And so that's a big hint that that's an electrophile, isn't it? That space is going to pull electrons into it, isn't it? Okay? Does that make sense? Okay. And that's what you need to do. These aren't going to have nice labels once we get past this half of the chapter, really. There's questions from like half a chapter, and those will have nice labels on. Okay? So there's not going to be a lot of questions where you would have to, and really you shouldn't have this. This isn't a thing that you're going to have in the real world, okay? Where everything's nicely labeled and tells you, I'm an electrophile, I'm a nucleophile. Okay? Yes, there are tables of them, and they will tell you relative strengths. But you shouldn't have to look. If you just look at the compounds, you should be able to tell. Okay? Okay, so again, we see some different examples. These ones just straight up make bonds, and nothing gets lost. See that? Okay. So in these ones right here, we actually lose things, don't we? So the nucleophile here is going to attack that carbon because it would have a positive charge, wouldn't it? Because it's bonded to the chlorine. See that? Okay. And so if we looked at that bond dipole, the carbon would have the positive charge, right? It doesn't actually have any space to accept the electrons at that moment, though, does it? See that? It's full orbitals. So when those electrons get sucked up into that carbon and start forming a bond, what's going to happen? Well, it has to lose a bond, doesn't it? And we have something here that has a pretty good difference in electronegativity. So the chlorine is going to take those electrons that were in that bond, okay? And it's going to go off by itself. We call that a leaving group because it does what? It leaves. Yeah, you gotta love chemistry. We would just name everything exactly what it does, right? Yeah, that's one thing I gotta say chemistry has done well on, is it has named things very close to what they actually are, right? Not a lot of like naming stuff after people, okay? By the way, if we look at this, one of the reasons we can say that this reaction would work really well, this doesn't seem particularly stable, does it? We don't see O minuses that are stable that often, do we? They tend to be very reactive, okay? But chloride off on its own, that's very stable, right? Notice that's that same stability that makes strong acids and bases for the previous acid and base scenarios, doesn't it? What makes HCl such a good acid? The chloride ion is very stable, isn't it? Okay? Hey, cool, huh? Everything's wrapping together. All those things we kept making you learn. Now you know why.
So with that third reaction, we just will remove the chlorine, add it to the other part of the reaction, connect the other two.
So these electrons are making a bond between the oxygen and carbon. These electrons are actually just coming off that carbon onto the chlorine.
So the chlorine would just be its own.
Yeah, chloride at that point would, yes, be its own thing. It's now a negative ion. And typically in organic chemistry, we oftentimes don't list the metal ions. And there would typically be like a metal ion in here. So this probably was like a sodium methoxide salt that we put in. And there'll be a sodium floating around, and now we have sodium chloride that's dissolved in our solution. Okay? We don't really care about those things, though, in organic chemistry. We focus on the stuff that we're concerned with. Because the sodium's just going to float around and do nothing, right? Do you guys remember spectator ions? The sodium would be a spectator ion. And so we typically work with net ionic equations in organic chemistry, but we don't formally state that. Okay? It's kind of a loosey-goosey thing we do a lot. It doesn't matter, though, because as long as your charge is the same on both sides, it's not a big deal. But yeah, the chloride will literally take the electrons that were in the bond and just float off. Okay? If this was not stable, this can come back and attack again. All right? In this case, the reaction will basically go to completion because chloride is quite stable. But if this was something that's not stable on its own, yes, it could come back and attack, and it would look just like this reaction. It's just we would reverse it.
So do we ever have to go from the reaction back to the product?
We'll have equilibriums, yes. That would be an equilibrium, where it goes both ways. But typically what we do is we draw it the way we want the product to form. So we flip it so reactants are on the left, the reactants we want to put in are on the left, the products we want to form are on the right. Okay? If it does go back and forth, we would put a double arrow, which means equilibrium, right? Okay? And that means it goes back and forth. And then we play games to make an equilibrium go the direction we want. Okay. Did you guys do the iron thiocyanate experiment back in Gen Chem? It was the spectroscopic, you made like red solutions, and you did Beer's Law? Okay. And you put like 10,000 times the concentration to make your standards? That's actually how you force an equilibrium to go basically to completion. Okay? That's what you guys were doing in that experiment. Okay, so this again is a nucleophilic base right here. This is a nucleophile acid here, an electrophile, acid right here. Again, notice that in this case, we're doing Lewis acid and bases, aren't we? So we follow the electrons. The electrons get donated to the proton, the hydrogen, which then leaves its electrons behind on that oxygen, which is the then resonance stabilized conjugate base here. And we formed our bond, giving us our conjugate acid. So notice many of the acid-base reactions we've talked about before with like Bronsted-Lowry also can be framed within the context of a Lewis acid and base, right? Okay. Though there are ones that are not Bronsted-Lowry acid and bases and Lewis acid base, okay? And Arrhenius acids and bases have ones that are neither. Like putting iron into water, right? Which generates H+, but does not fulfill the context of Bronsted-Lowry acid or base. Okay. So now we're going to talk about some of the naming. Again, the naming is the base of everything. There are very few questions that you're going to be able to accomplish and that you'll understand at all without being able to name things, right? Because without the language, you can't even think of it. Okay? Language and thought are the same. So, hydrocarbons. These are different types of hydrocarbons. Hydrocarbons means carbons with hydrogen on them, right? And so alkanes. These are going to have single bonds between the carbons. All carbons are going to be sp3 hybridizations. That means they're tetrahedral, okay? That means alkanes make a zigzag pattern, don't they? If you look at the carbon-carbon backbone. Cycloalkanes, again, these are going to have that sp3 carbons, but they'll form a ring. So they have to connect back into themselves to form a ring. Cyclo. Like, cycles. Okay. Alkenes, these are going to be double bonds present within the molecule. It does not mean that you have all of them having double bonds, but it doesn't mean that you doesn't have to just be one. It can be one, but it doesn't have to be. Okay? And so double bonds are present. That means that you have at least 2 sp2 carbons. Okay? Because the double bond has to be sp2 carbons. Because the double bond takes up a p orbital from each carbon. So there's not a p orbital to mix in the hybridization, right? Okay. Everybody remembers how you get hybridizations? It's literally just counting up the bonds. So if you count up your orbitals, that gives you your hybridization. Okay? So if all of them are available to make single bonds, you have 1 s orbital, 3 p orbitals, And that gives you sp3, doesn't it? If you've consumed one of the p orbitals because you made a double bond, that gives you one s orbital and two p orbitals, sp2. If you've consumed a p orbital, two p orbitals to make a triple bond, which is how you make a triple bond, right? You do it in one direction and the other, then that gives you an sp orbitals left, right? Meaning you have to have sp hybridization for that carbon. Okay, so cycloalkenes, guess what those are? Double bond in a ring. I know, right? See the patterns? Alkynes. Everybody practice that with me. Alkanes. Say it with me. Alkanes. There we go. Very good. Stress that ane, right? Okay. Unfortunately, you guys have a speech impediment, which is called Tennessee accent. Or maybe Alabama accent. So Southern accents typically are some of the most difficult to understand in scientific language. And unfortunately, people will judge you based upon your ability to talk, right? Because it's one of the few things they can judge in a first meeting. So be careful here, because it will trip you guys up and it will make people underestimate you. Okay? Alkenes. Nope, careful. Don't, see, that's the problem actually. A lot of the Southern accents, you guys will get the alkenes, so it sounds like alkynes. Okay? And you won't be able to tell the difference, even if you have two Southern people. Neither one will be able to communicate. It's like Indian. So, alkenes. Okay, see how I'm stressing the "n"? Okay. Alkynes. Ines. Kynes. Very good. Yeah, I know, it doesn't feel natural to you, does it? Yep. See, the ines in the Southern is very similar to the enes, right? Yeah. So, yeah, practice those. Make sure that you can actually say them, because you will need to be able to say them if you go to PA med school and such. And if you say them wrong, people are going to think you're dumb, even if you're not dumb. Okay? Which is sad, because like there's a very long history of very high quality scientific programs in the South here, in Tennessee specifically. But, everybody thinks they're dumb because they have the accent making them sound like they have two things the same. I don't know. And I think you guys play into it sometimes with the slow Southern boy draw. Yeah. So anyways, alkynes, guess what those are? Triple bonds. If you have a triple bond, that means you have an sp hybridization, doesn't it? So a single triple bond means you have at least two sp carbons. Aromatic. Aromatic means it's going to have a benzene ring, or more specifically, it's going to be benzene-like. Does anybody remember benzene? It's the one with the alternating single double bonds, right? And those give you a resonance structure around the entire ring. Okay? We'll go into more details on aromatic compounds and aromaticity throughout the 2 semesters. And it's actually a kind of an interesting subject by itself. Okay? So this will be quite something. All right, so the alkane naming. When we get to these alkane compounds, we name the different carbon chains based on their length. And they have these prefixes, and then the last part designates if you have an alkane, alkyne, alkene, right? Okay. One of the things you need to remember is I'm going to teach you naming here. This naming is primarily going to be IUPAC naming, which we'll get into in a bit. That's the most important naming to have down. As long as you are mostly on with the pattern, everybody will know what you're saying, okay? Even if you don't get the minutiae correct, because it has very fixed patterns. Whenever we name these things, we're always going to concentrate first on what we call the parent branch, okay? It's your longest branch. It's where everything else is attached to. These are just straight chain versions right here, and so there's nothing else to worry about. We're starting soft. Okay, so methane, me for one, right? So methane. Ethane. Anybody know what et al means? Two or more, yeah, exactly. It's what you use when you have two or more authors, right? First author et al. Okay. Eth, right? Ethane. Propane. Does anybody know what a pro baseball player's considered the best batting score you can get is? 0.3. 30% hit rate. It's the only job you can be world class, renowned, and you only get right 30% of the time. Yep, and so you're a pro baseball player of 30%, right? 3. Okay. Butane, how many cheeks do you have? 4. 2 on the top, 2 on the bottom, right? Okay, so 4, butane. Now tell me you don't remember that. It works, right? Yeah. Pentane. Pentacle, pentagram, pentagon, right? 5. Okay. Hexane, hex wrench, hexagon, hexagram, I guess, also. Again, 6, right? Those are the ones that people usually know pretty well. Heptane, again, there's not a really, really great one, but again, heptagon, hep is 7. Okay, so heptane is 7 carbon chain. Octane, everybody knows octane pretty well, right? Yeah, octagon. Yeah. Octopus, 8. By the way, octopi can have more than 8 tentacles. If you subdivide their tentacles, they'll continuously grow new ones. And so there's been octopi with hundreds of tentacles, which that should give you nightmares. You know, octopi are incredibly intelligent too. Sometime have me tell you a story about the smartest animals on the planet. It's creepy. Okay. Nonane. Non was actually a goddess of fertility. How long does it take to have a child? 9 months. Nonane, right? Decane, decade, right? Okay. Decimal, 10. Dec, 10. So decane, 10. We'll go a bit more into these right here. There's different prefixes you can use on these that tell you that instead of being straight chained, they're branched. Okay? If it has a shape like this, a V at the end of it, that means that it's an iso. Okay? And so this has a V where it's 3 carbons make a V at the end of it. And so that is isobutane. Okay? You guys probably have heard of isopropyl alcohol. Guess what that has? It has an alcohol, which is the functional group. What sort of carbon chain does it have? Yep, an isopropane, right? So basically just drop one of these carbons, replace it with an alcohol. There you go. Isopropyl alcohol. By the way, all of the chemical names are either common names for historical reasons. If they're newer ones, they're derivations of this naming scheme I'm going to teach you. Okay? And so if you just look at a drug name, you can actually tell large parts of what's in it. Okay? What it's composed of. Again, this right here is the cycloalkane. This would be it written completely out so you can see everything, carbons and hydrogens, though it doesn't give you a 3-dimensional structure, does it? This right here is your line angular method of writing. And so this is by far and away the one I would expect you to use. Does anyone remember how you figure out the hydrogens? Yeah. So the hydrogens just fill in the number of bonds, right? So each carbon should have 4. They have 2 bonds going to other carbons, and so each carbon has 2 hydrogens here. Okay?
Does it need to draw the hydrogens on that?
Here?
Yeah.
Not unless you're specifically gonna do something with them. Okay? Most of the time you're just gonna do this. If you're specifically doing a reaction with that hydrogen, then you would have to draw it out, but not any other hydrogens. This right here, again, cyclopentane. How many carbons are in it? 5. This one has 6 carbons, so it is cyclohexane, right? It's cyclo for what reason? Yeah, in a ring, right? There you go. Okay, we got a double bond in there. And so what's that? Alkene. So this has 2 carbons. That would be ethene. We have 3 carbons. That would be propene. Yeah. Now, propene is actually the correct IUPAC naming. There is legacy naming for many of these things, and this would be more of the common name for it. Okay? Which is propylene. Okay, so a double bond is going to have a position, isn't it? Not everything's the same. We got one of them that's a double bond, don't we? And so on 2 carbons, we don't have to tell where it is because it can only be one place, right? Okay. On 3 carbons, it doesn't actually matter if it's on the left or right here, does it? If it was on the other side, we can just flip it around, can't we? It's symmetric. And so we don't have to actually say where it is because it wouldn't matter. How about 4 carbons? So we could have it there, right? But we could also have it in the middle, can't we? And those would be different, wouldn't they? See that? Double bonds in different places. If we had it here, by the way, we would just flip it. It'd be the same as this one, wouldn't it? Okay, and so when we have it where it would be different, 4 or more carbons, we have to specify where it is. Okay? Now, unfortunately, the IUPAC naming committee are kind of insufferable pains in the butts. My advisor, who outdated the IUPAC naming committee and was a very famous and influential scientist, said they're right bastards. That's what he used. And in fact, they got into a fight for like 10 years and refused to do anything. So they do have some interesting history there if you actually start looking into it. But anyways, there is new and old IUPAC naming. They've redefined things, sometimes with no real reason for it. Okay? So this is the new IUPAC naming methodology. So you would put but 1-ene. The 1 is the first carbon as you would number them from left to right that would have the double bond. And you always organize your functional group, in this case the double bond, so it's the lowest number possible. Okay? And so you don't have to say 1, 2. You just have to say 1. Okay? Because if it's attached at 1, it has to be attached with 2 as well, doesn't it? So, but 1-ene. Everybody want to try that with me? But 1-ene. I know. Kind of a pain. The old way, by the way, was put the 1 in front. So you would have done 1-butene. Which flows much easier when you say it. But whatever. I get why they put it here. You know, it corresponds to the functional group then, doesn't it? This one being but 2-ene. But 2-ene. Everybody with me? But 2-ene. Okay. And that means that starts on the second and goes to the third, doesn't it? Can you see how you never can be confused about going from 2 to 1? Because it always has to start the lower number, right? Okay, does anybody have any questions on those so far? Very good. Make sure you practice right away. This is a language part of the class. If you don't practice the language after you learn it, guess what happens? Poof. And that's wasted time, right? So if you practice this right away, then you'll spend maybe 2 hours practicing it. If you practice this a week from now, you'll spend 4 hours. Okay? If you practice it 2 weeks from now, you get like 6, 8 hours. Yeah, you've lost everything, right? Okay. These are the alkenes. Again, it's the same sort of rules, right? So 2 carbons, alkene, it's going to be ethyne, right? Mm-hmm.
Top is alkenes, but the bottom is alkynes.
Oh, yeah, I have mislabeling. Here, let me actually fix that real quick. Okay. Nope, you are correct. That happens. Hopefully one day I'll have everything fixed. Okay, so alkynes again. So again, 2 carbons would be ethyne, right? Everybody with me? Ethyne. Come on. Ethyne. There we go. 3 carbons would be? Yeah, propyne. You got it. When we get to 4 carbons, we have to specify where that triple bond is, don't we? Okay? And so, but 1 ine. Mm-hmm.
That's only when you get to 4.
It depends on how many unique cases you have. So basically, you can always specify. That's actually not, it's just like a weird language thing if you do. It's like putting an unnecessary A in, right? But when you have it enough cases that there's 2 or more options for compounds, then you have to label. Okay? Otherwise, if there's only one option, you can just assume it's on that option. It has to be. Does that make sense? Okay, so this is actually acetylene, by the way. You guys know acetylene torches? You know the welding torches people use? They're called acetylene torches. The tank is acetylene gas. That gas? Okay, that's the common name for ethyne. Yeah. Because they used to call it acetylene for the triple bond, and then you would name the chains off of the acetylene. Okay? And that was before the standardization, that's the IUPAC naming. It's kind of why they had to do it. It's because they had multiple names for the same compound. And nobody knew what the hell you were talking about. We'd have 4 or 5 publications, same compound, same thing, and people would be like, not even knowing they did the same stuff. It was a mess.
Sorry.
Mm-hmm.
As far as the exam goes, will there be like a lot of labeling, or will it mainly just be we need to know it for the question that's going to later on?
I mean, at first there's going to be some. So the exam, I'm going to have 1 or 2 questions about just naming, pure naming. But in the future, oftentimes what you'll see is like, I want you to make a mechanism for taking this name and creating this name. Okay? And so without the naming, you won't know the structure and you can't do the mechanism. That's more of what would happen. Anyways, I think you guys got that. Any questions on the naming for triple bonds? Okay. This right here is your aromatic compounds. Again, here's a benzene ring. Remember that alternating single and double bonds. That actually doesn't mean that there's a single and then double, then single, then double bond. That means that there is a resonance structure, which is like 1.5 bonds on each, right? So each of these has a little bit of double bond character, a little single bond character. Okay, this right here is what's called a benzene derivative. And again, it would be an aromatic compound, and that means you have different groups attached to the benzene ring. Okay?
So you wouldn't,
Mm-hmm.
so it's separate, that's why it's ethyl benzene. You always have that at the end for every.
Yep, you'll have benzene will be your parent in this case. And then you have a substituent off the benzene, which will be, I'll get into the naming of that. When we do these substituents, they have the same pre-part, met, eth, but they're going to end in "ile," and that means it's a substituent. Yeah. And so in this case, it's ethyl benzene, an et group substituted on a benzene, right? And this is just the generic alkyl benzene. By the way, does anybody know why these are called Rs? Have you guys seen those before? Should have seen them in Gen Chem. No? Okay. Okay, if you don't want to specify what that is, you can put a bond to it and then say R. Okay? And that basically specifies that this is some sort of alkane-ish group. Okay? So some sort of alkyl group. It could have double bonds in it. Maybe it doesn't. It's just some sort of carbon chain. Okay? A generic one, whatever you want. And that R group stands for residue. So if you were to break this apart, that would be the residue that would come off. Okay? And that's what that means. If you have a functional group, it's going to be like an X, a Z, or a Y. Okay? That means this is a functional group that's not carbon chains. Okay? Okay, so let's talk about compounds containing oxygen. You guys already brought up one, which is alcohol. Tennessee's famous for this one, isn't it?
Moonshine.
Yeah, moonshine. Anybody know the alcohol? It's in moonshine, beer, and you can drink? Ethanol, exactly. Anybody know why alcohol, like Tennessee moonshine, sometimes gets a bad name?
What?
The one that, the alcohol that it causes blindness. Okay, so you know that moonshine that's not properly done can cause blindness, right?
No.
Yeah, it can. And if you don't separate it properly, it can cause blindness. Though you really have to screw up. And that mostly comes from very cheap operations back in the Prohibition era, where they would literally give you wood alcohol. That's the public name for that. And they do that because they couldn't get real alcohol because they got busted. The ethanol, right? Anybody know the name for that alcohol? Anybody know where it comes off in the distillation process? The one that would cause you to go blind. It comes off at the pre. You know how you always get rid of the first jug? Okay. It's methanol. You get rid of the first jug because met means one carbon, right? Eth means two. Eth weighs more, doesn't it? And so the methanol comes off first along with the acetone. Okay? And then you get a good stretch of the ethanol, which is the moonshine that you would normally drink. And then you have the tailings, right? And the tailings, the stuff weighs more. Okay? And there you go. That's moonshine. We actually will, kind of.
Really?
We did.
Yeah.
We already did.
Yeah, we'll distill it.
Oh, we're gonna.
Yeah, we'll distill alcohol to higher, instead of doing a hydrocarbon, which is more dangerous and kind of not fun because it smells, I'll have you guys do an alcohol. Technically, we're going to make grappa, which is a concentrated wine. So technically, that's what we'll actually make. But I wouldn't recommend it, just because we're not careful enough, and the glassware is used for other things as well. Yeah. And it's not going to be large amounts. Like, you would get a thimbleful. We're only going to do like a thimble. Because keep in mind, like moonshine setups take weeks to get right? And you have to like tweak everything. You guys are gonna set up and tear it down in one day. If we were gonna do a moonshine operation, you'd be tweaking that moonshine operation for a week or two to get it to work right. Mm-hmm.
So, I know this is kind of not related, but
Yeah.
it's about moonshine. So why did they distill it and why are they doing it in places that are so secluded?
Government taxes. Okay, so it depends on what period you're talking about. There was Prohibition. By the way, do you guys know who started Prohibition? It was the first women's right group. So before women got the right to vote, they got Prohibition. Which is, it makes sense if you look at that time period. It really makes sense, but really. But it actually is pretty weird, right? Prohibition before voting. But during the Prohibition era, they did it because it was just outright illegal. Okay? In fact, you could get heroin, but you could not get alcohol. Yeah, cocaine and heroin were legal, but you couldn't get alcohol. Yep. Yeah, it's pretty crazy, right?
Were people overdosing?
Oh, yeah. Well, people, to be fair, it was a different culture for being a heroin user. When it's legalized and you can get it from a pharmacist, they'll warn you of things not to do and give you processes that you can keep yourself from overdosing and it destroying your life. Drugs typically are not as bad when they're legalized but monitored. Though war on drugs may have actually caused more deaths than anything. But whatever, that's a whole nother conversation. Nowadays, the reason that you have illegal moonshine operations is one of the largest sources of revenue for the federal government is taxes on drinking alcohol. That's one of the reasons why it's illegal, in fact. And you have things like marijuana and stuff that are illegal in the federal government level. Because alcohol and marijuana are actually health-wise about the same. Alcohol would be a little bit worse for you in the long run, but really only because of the liver damage. The marijuana actually causes more mental damage, as it turns out. That's recent studies, by the way. So, okay. The alcohol that's why if you ever have one of those moonshines that get busted, you don't get raided by the local police. You get raided by the Food and Drug Administration. They have assault rifles, the military-grade weaponry. And, they body armor. They look like the Army. Yeah, because they are. They're the federal army. So, yeah, and that's why if you ever see the ethanol pumps, California tried to do ethanol in the pumps, just straight ethanol. They have to actually put an additive that would make you sick if you drink it. Because that's the only way they can get around the federal tax, which increases the cost of alcohol tremendously. Yeah. Yep. And the reason that alcohol can now be added to gasoline to increase its octane rating is actually because they lost the food pyramid to force you to eat corn. So they needed something to use all the damn corn. Yeah.
Thank you. I'm sorry. My mind is...
No, that's okay. It's actually a fascinating topic, but I can't waste your guys' time for the class. Sorry. Anyways. So again, alcohol is going to contain a hydroxyl group. The hydroxyl group is an OH. Okay? This is going to be the main functional group for anything that we call an alcohol. Ethers are going to contain two alcohol groups that are bonded to an oxygen. The easy way to remember ether is either side. Okay? So you have an oxygen with carbon chains on each side. Ether, either side.
The alcohol groups, is that alkene?
Yes, alkanes. It's some version of alkane, alkene, alkyne.
Okay.
Yeah, it has carbon chains on either side. Okay. Alkyl just means it's substituted on. Okay. Aldehydes and ketones, these are very similar. They're going to contain what's called a carbonyl group. Carbonyl groups are the C double bond O. Okay? The difference between these aldehydes and ketones, I'm going to do when I have a picture up there for them, okay? But basically, it's whether you have a hydrogen on that carbon here. Okay? What's up?
So I used to do keto, and it was all about ketone levels.
Yep.
So if your ketone levels are super duper high,
It can be, yes. Really, okay, so it does affect in long term if your ketone levels are high. You can then have problems with your liver in the long run. Okay? But you can actually kind of get around that by taking more of the enzymes that break down ketones to help yourself. But yes, it's not a good idea to have high level ketones. Okay?
at least for a long time.
Not for long periods. Long periods, though, depends on the person. So people that are better at breaking it down, break it down faster, can do that for like years. People that are bad at it, you could do it for like a month and have liver damage. Okay? Whenever you think of humans and biological organisms, anybody know what the Pareto effect is? No? Okay, so basically, if you look at any population of biological organisms, 50% of the top, so like 50% of the money, is going to be made by a square root of that population. So out of 100 people, 10 people will make 50% of the money. Okay? Out of 100 singers, 10 singers make 50% of the songs. Yeah. And that actually goes on for infinity. So out of those 10, one of those makes 50% of that. And so on until you run out of, ones. Singular individuals or singular cells. And it works all the way through, up and down, societies, individual organisms, their cells, everything. Okay? So like liver function is that same thing. Like there's a top 10 out of 100 that is almost impossible to damage their livers without something really crazy happening. Yeah. And the reason for that is not actually the aldehydes and ketones. It's if you have too many of them, your body will start processing them to things like acetone, which will then destroy your liver. Okay? So the ketones, if your body didn't screw up, would actually not be a big deal. You have lots of ketones and aldehydes as compounds in your body. Okay. Carboxylic acids, these contain the carboxyl group. That's the COOH. Remember acetic acid? Vinegar? That's that. Okay? We just saw it a little while ago. Okay, so here's an alcohol that shows you a bunch of different examples, and it shows you the hydroxyl group right there being attached. This is the generalized form of an alcohol, which is R, meaning some sort of carbon chain, with an OH group attached, right? Here's a specific version. This is wood alcohol. This is methanol, is the IUPAC name, or methyl alcohol being the common name. And notice it has one carbon attached to the OH, right? Here's isopropyl alcohol, by the way. It has 3 carbons attached to it, which is where you get the prop, or otherwise known as propane-to-all. This is how you do the IUPAC naming for alcohols. Instead of the last part, which is E, you are instead going to put an OL. The OL stands for the alcohol. You drop the E so you can actually say it. Anybody want to try to say propane-ol? and have the E there? Propanol? You can't really do it, can you? Because it's vowels. Yeah. Your tongue can't make the two shapes. You had to separate them. See that? Propanol. Okay. So try to say that with me. Ethanol. Be careful you don't say ethanol. Okay? It needs to be an O. Okay, methanol. Methanol. Okay, everybody say the other one, which will be methanal. Methanal. Okay, very good. Methanal is not an alcohol. Okay, we'll get to it in a bit. Okay, so again, that's the alcohols, that's the hydroxyl group. Does anybody have any questions? Nobody? Nobody saw this N right here? What is the N? Nope. It means normal. Yeah, yeah. So a small N means normal. Okay? And what that means is that's just the straight chain. All right? So notice that this is the straight chain version of propanol, right? This then is the branched version. Cool, huh? Okay. Does anybody have any questions? Nothing?
You said that's the straight chain version and the French version, so why is that one and that one two?
So this one's connected at the first position of the carbon. So that would be carbon 1. When you're doing any functional group, it's going to be labeled based on what carbon it's attached to. So in this case, this OH is attached to the first carbon.
I know we do that earlier with
The double bonds and
but it
triple
was
bonds.
with the bond, like the double bonds. So
Exactly.
I didn't see the double bonds.
So the double bonds were a type of functional group. This is the next type of functional group we're going to cover. And by the way, that's how this chapter is structured, in case you're curious. There was the double and triple bonds. And now we're going to the other types of functional group. These are the oxygen ones. Then we'll go to the others. Okay? And so this right here, again, is attached to the first position. This one here is attached to the second position. See how that would be 1, 2? And whenever you number the carbons, you always get a number, so you have the lowest number on your functional group. Okay? By the way, there's actually a part where I'm going to have this more structured explanation for this. But unfortunately, the naming, to give you examples, I have to give you the examples with the names.
So do you start from right to left?
It doesn't matter. It isn't right to left that matters. What it is the lowest number for the functional group. So whatever number gives you the lowest number for the functional group, that's how you number these carbons. So for example, if I went 1, 2, 3, that would give me a 3 for the OH. So I need to go 1, 2, 3. Okay? Not if you follow the rules, which is giving the lowest number for the functional group. Yeah, that's why that's the rule. Well, it's not weird because you can write it in any direction. So this molecule can be rotated in any direction in three-dimensional space, right? So for example, I could say that the handle always has to go first, or I can look at the handle going last all the time, can't I? Okay? That's because in reality, this object is the same either way, isn't it? Same thing happens with molecules. We're Yes, they could name it incorrectly. You can very much name it incorrectly. Though, notice that if you do follow the IUPAC naming conventions, once you started writing that out, you'll be able to write it out, and then you go, well, that was wrong. Like, you'll still get this, and then you go, well, they named that wrong. These are conventions to give you a quick way of identifying these. Okay? Mm-hmm.
I had a question about Pearson because these look kind of similar to some of the things that I had to try to do. But how do you get it to do specific things? Because it didn't make sense to me how I got one of them right.
You're gonna have to, like, that's the question's too broad that I can't answer you. Bring in the Pearson and actually show me, okay? Yeah. when it comes down to Pearson, you really got to show it and play with it in front of me so I can show you where things are going off. And once you get the Pearson down, it'll be easy, but you got to do it once first. That's the hard part. Okay, so that was the alcohols. These right here are the ethers. Notice the ethers have oxygen that's going to be between two alkyl groups, two carbon chains. They can be many different types of carbon chains. They don't have to be different carbon chains. They can be the same ones or they can be different. It doesn't matter. Either way, it's an ether. Okay? It can even be in a cyclic compound. We can have a ring. Okay? And so that's furan. That's an ether. See how it has a chain? So it has carbon chains on both sides.
You expect us to remove that?
You will at the end of this, the entire semester, you'll definitely remember it. But yeah, again, remember that these are examples. These are not me giving you things you need to learn right now at this moment. Okay? So right here we have diethyl ether. That's actually the common naming. The common naming you would have went diethyl. Di meaning two, ethyl groups on each side. This is that hydrogen bonding of that ether. Notice that ethers have hydrogen bond acceptors, but no donators. Okay? So ethers tend to not have the hydrogen bonding going on when you just have ether. Okay? Aldehydes are then ketones. So remember, these will have a carbonyl group. The carbonyl group is a carbon-oxygen double bond. The difference between a ketone and aldehyde, a ketone has that carbon where it's filled with other carbon bonds. Okay? So that carbon will have two carbon bonds to it. An aldehyde, on the other hand, will have one of those spots with a hydrogen. Okay? And so that would then be aldehyde right here. By the way, the reason I made you pronounce ethanol, ethanal, aldehydes are ethanal. Okay? So two carbons with an aldehyde at the end is going to be ethanal. The hydroxyl group would have been ethanol. See the difference there? The acetone, which we just mentioned, boxing and destroying your liver, that is a ketone, and that is propane 2-one. Okay? Or if you were to do that all in one without the number, it would be propanone, is how you combine that. Okay? Okay, and that's ketones and aldehydes. Both of them are carbonyl groups. Anything where you have a carbon-oxygen double bond is referred to as a carbonyl group. Okay? You can have other things attached to it as well. For example, you have a carboxylic acid here. So this has a carbonyl with a hydroxyl group attached to that same carbon. Okay? And so you have the carbonyl with the hydroxyl group attached to it, same carbon. That gives you a carboxylic acid. Guess what they are for acid and base? Acids. They're acids. Remember the resonance stabilized acids that we gave you examples of? Those are carboxylic acids. This right here, by the way, is methanoic acid, otherwise known as formic acid. Anybody know where you see this? Anybody been bit by a ladybug or an Asian beetle? Okay, it has a kind of a weird smell when you kill them too, or they bite you. That's formic acid. It tans you like leather gets tanned. Okay? This right here is acetic acid, vinegar, which gets used in basically all the food down here. For some reason, vinegar is very popular. Anyways, there you go. Notice that carboxylic acids always have to be at the end of a chain because your carbon can't have two bonds to carbon, right? You've consumed 3 of the possible bonds in carbon. Okay? By the way, aldehydes also always have to be at the end of a carbon chain because you've consumed 3 bonds to make an aldehyde. Okay? Okay, we'll start up here next time. You all have a great day. I'll see you Thursday.